Hello everyone and welcome back to this next lecture. So in the previous lecture, we had introduced stability as a definition with respect to control systems. And we had given some examples of stability in the non-engineering sense by driving a car. We took a few examples from different domains and we talked about stability and we defined how stability is. That is, stability is the ability of a system to withstand a disturbance and recover from a disturbance. Now, let us try to bring those definition of stability into this control system that we have, and especially this because this is the problem that we are trying to solve. That is, this is of a grid connected system. So now, for this, all we have done is I've taken the block diagram that we did in the previous few lectures, and I've made one generalization. Everything else remains the same except for one change. I have replaced the inductor with a plant transfer function denoted by G of S. Right? This G of S is just the resistance and inductor combination. It's basically 1 upon R plus SL. If you want, just compare this block diagram with the previous one. There has been no change except for this one change. Alright? So, simply speaking, this is one example of a closed loop system. It is possible in many closed loop systems that we could have inputs from very other different parts, right? It is possible. In your case, you might have a slightly different system. Now, let's take this system and let us look at how this system is affected. So for example, now if we have a look at this closed loop system, once you close the loop, right, you have changed the system significantly. Right? For example, if you take this one look, if this closed loop system, there are several variables that have been denoted. There is a reference, there is the error, there is the controllable voltage, there is the grid voltage or the disturbance voltage, and finally, there is the current output. Now, in all these variables, the only variables that are provided externally to this system are the reference and the grid voltage. These are the ones that are independently provided to the system. All other variables are internal and they are calculated. They are not provided. Right? The error is calculated from the reference and the output. The controllable voltage is calculated from the controller. Right? Everything. Only the grid voltage and the reference are now inputs to this system. So therefore, the closed loop system is affected by two signals, the reference and the grid voltage. These are the new inputs to this closed loop system. So now if I want to express this current with respect to these new inputs, which is the reference and the grid voltage, I can just do that calculation. Say for example, I can calculate the error, that is Iref minus I, feed it to the controller. The product of the controller and the error is this controllable voltage, which subtracted with grid voltage and multiplied by the plant transfer function gives the current or the output current, right? So therefore we have now a simple equation. All we have to do is rearrange this equation, and if you rearrange this equation, all we have to do is take out this term, bring it to this side, and take the common factor and bring it to the denominator. The result is we have now expressed the current, output current, with respect to the reference and the grid voltage. Alright, this is something we had also done 2 lectures previously, but I am now doing it only with respect to transfer functions. So if you look, each term, that is the dependence of the output on the reference, is dependent on or rather varies with the plant model, that is G of S, the plant transfer function, and the controller transfer function, K of S. Right? We have taken this as a PI controller, but we can take any controller we want. That's okay, right? So this transfer function decides the relationship between the reference and the output. And if you look, we have a similar expression, except there's one term missing. If you look, the numerator, the denominator is the same. The numerator, the controller transfer function is missing from this second term. Right? So the second term denotes the relationship between the grid voltage and the output current. And this entire expression decides how these two variables impact the output. Alright, so far so good. Now, with respect to this, you will see that there is one term that is common between them. That is the denominator. They both have the same denominator. So you can actually write it as a single expression with the same denominator. Right? I just wrote it this way because this is a very common very common way of writing any control system. That is, with respect to the reference and with respect to a grid disturbance input. So let's talk about the denominators. So if we can use this equation, right? Use this equation and we can define two transfer functions. There are two different transfer functions which we can denote from this particular equation. One, as I said before, is the relationship between the output and the reference. That is this one. And the second one is the relationship between the output and the disturbance. So you could say that this first transfer function determines how the output will behave with respect to a reference. And this will decide how the output will behave when the system is subjected to a disturbance. Now, think about what I said in the previous lecture, that system stability can be defined in two ways. That is, the impact of a disturbance on the system. This disturbance can be at the reference or it can be through an external input. So the disturbance can be at this reference or it can be at the grid voltage. In any case, this transfer function should be able to tell us how this output will behave in the case there is a disturbance in either of them. Right? These are the two transfer functions that we can use. Right? So what we usually do, we study the impact of one variable at a time. So if you are looking at the impact of the reference, we will ignore the grid voltage. And similarly, if you are studying the impact on the grid voltage, we will ignore the reference. Right? Usually one at a time. That makes it less complicated. Right? And if you take both into account, we will have the sum of the effect of both variables. Right? This is the effect of an LTI system, that you can study them separately and just bring them together. So let's keep going. Now, if you notice this term 1 plus GFS KS, this appears in both of them. Now, this term that shows up in the denominator has a very special name. It's called the characteristics equation. Right? Now, this characteristic equation has a huge impact on the behavior of the system. Right? And the roots of this characteristic equation, that means the values of S for which it becomes 0, that is usually the root of any polynomial. The value of any polynomial in a variable, the root of that polynomial is the value of the variable at which it becomes 0. Right? So therefore, the roots of this characteristic equation are the poles of the closed loop system. So if you look, whenever this becomes 0, the denominator, this becomes infinite. This entire transfer function becomes infinite. So the values of the frequency for which the denominator becomes 0 makes the transfer function infinite. And that is called a pole. That is denoted as a pole. Now the poles, as I said before, of the characteristic equation have a profound impact on the behavior of the closed loop system, and especially stability. Right? So that means that all the stability discussions that we did before actually boil down to this one equation. Right? When we wanted to talk about, in the previous lecture, when we talked about how stability can be with respect to change in reference or change in grid voltage, both of them have this same term. Whether it's the reference or the grid voltage, they are affected by the same term. So all we have to do is study this one characteristic equation, and we know how the system will behave if there's a glitch in the reference or there's a glitch in the grid voltage. This is exactly what we wanted to study. And this is what is called stability analysis. Now, in the next lecture, I'm going to talk about how poles of a system, any system, are going to impact the stability of the system. Because before we directly go into stability analysis, we need to understand this relationship between poles and behavior of a system. Right? Because now we are mapping the behavior in two different domains: frequency domain, time domain. So if we know that this is the frequency domain equation how will the corresponding time domain equation look like? That is what we're going to study, and we'll take some very simple examples. So with this, I'm going to end this lecture. Again, it might be getting a little confusing because, as I said, we are just connecting the dots together. We are slowly building up a narrative for system analysis and stability analysis and control design. So if any of this is confusing or you have any doubts, always post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture. Thank you so much and see you soon. Goodbye for now.